Capstone Team Epicenter Engineering, representing the San Diego State University Earthquake Engineering Research Institute, has completed a project involving the design and analysis of a 28-story high-rise to be located in San Diego, California, in the Kearny Mesa community, replacing the existing San Diego planning and land use. The structural component of the project was done so in regards to the EERI seismic design competition rules. All other components of the project, such as the foundation investigation, the drainage study, and the construction management, are designed for legitimate purposes. Epicenter Engineering was given the task of performing a geotechnical investigation for the proposed Claremont Tower. The building is to be located in San Diego, California, replacing the existing San Diego planning and land use. The site of the proposed structure is located primarily on the La Mesa Quadrangle on Geologic Unit QL, the Linda Vista Formation. The formation soil layer is predominantly composed of reddish-brown, coarse-grained, interbedded sandstone and pebble conglomerate. Boring logs for the existing SD planning and land use were unattainable. Therefore, borings from a previous project, the Scripps Memorial Hospital, La Jolla, was used. Using the boring log, a shear-wave velocity was calculated for the structure's location, and the site was then classified as Site Class C using the United States Geological Survey Seismic Design Map application. Site Class C means the area has a soil profile of very dense soil and soft rock. While the site is not located along any seismic fault lines, it is located 5.02 miles northeast of the Newport-Inglewood-Rose Canyon fault zone. The proposed site is located in seismic zone 4, with the magnitude most likely to occur on site being 6.78 on the Richter scale. This was determined using the USGS deaggregation map application. Epicenter Engineering found one-way concrete mat slab foundation to be the most sufficient foundation for Claremont Tower. In the event of an earthquake, the benefit of using mat slab foundation is that the entire structure will move uniformly as it is all under the same foundation. This structure's foundation will be square and will encompass the entire building plan. First, the total loading of the building was determined to be about 23,695,500 pounds. This value was incorporated when solving for the allowable bearing capacity. The bearing capacity is the capacity of the soil to support loads subjected by the structure. The value came out to be 241,157 pounds per square foot. This high value shows the foundation is more than sufficient to support the loads applied by the proposed Claremont Tower. The area of the foundation is 300 feet by 300 feet. Using the Navy Facilities Engineering Command Soil Mechanics Design Manual as well as the ACI 31808 building code requirements for structural concrete, calculations found a 3 feet thickness to be sufficient for the foundation. However, Epicenter Engineering decided to use a conservative 5-foot thickness plus an additional 6-inch sand base. The sand is to be drained or sandy gravel, which will be spread below where the concrete is to be poured.
For the structural analysis of the model, the structure was taken as portraying a linear elastic behavior with a maximum bending stress of over 26,000 psi. The structure was subjected to 3 ground motions, the first being a scaled-down depiction of the El Centro earthquake, the second being a Northridge earthquake, and the third being a simulated or computer-generated earthquake. The material properties used for the analysis is taken from an average of the maximum and minimum ranges for balsa wood, thus analyzed as medium density. After analysis, the maximum deflection shapes of the structure depict that a failure would most likely occur in ground motions 2 and 3. As mentioned earlier, the maximum bending stress of a quarter-inch by quarter-inch medium density beam is over 26,000 psi. As noted from the data, the vertical columns are subjected to stresses beyond that in ground motions 2 and 3. We will revisit the design of the model and incorporate a truss spiral to dampen the vibrations, and shear walls to assist in resisting the strong lateral forces.
Now moving on to the design component of the Claremont Tower. The building features 4 main columns located here, 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 and here. 28 regular columns located on the exterior as well as the interior of the buildings. 28 floors. The chevrons, and the small moment frames located in the middle of the exterior frames of the building. And since the building is symmetrical, you can see these features throughout every faces of the buildings. Now let's look into the detail of the structure. Now the four main triangle columns were designed as a complex truss systems, as you can see here, to offer the maximum resistance against the lateral forces from the ground motions. Due to its nature, the triangle columns were able to shoulder the overburden stresses from the sudden failure of any structural members. In addition, the chevron, right here, were designed to protect the outer frames of the structure. As the structure oscillates side to side due to the seismic ground motions, these chevrons play a crucial role to transfer all those lateral forces to the columns, then ultimately to the ground. During the competitions, the structure will be loaded with 2-pound weight bars, alternately between each floor. In order to distribute those load evenly, these moment frames were designed to fit all the weight bar tightly, as well as preventing the structure from drastic sway. Our main goal is to transfer all the seismic load effectively throughout the buildings and secure its safety for the duration of the building's seismic performance. As mentioned earlier, our current design is inadequate for competitions, so therefore we have decided to add a few new features for the proposed design for ELI competitions. On the left here, you can see this is our current design that are currently being built to test out the performance of the columns in pink here. On the right side is our proposed design for ELI competitions. Let's look into the detail. The design were kept the same. As you can see, the floor plans are ultimately the same. The new things that we are added are the spiral in red here, as well as the shear wall. We believe with these new features we will achieve the stability that the structure needed to resist the ground motions that will be subjected during these competitions. Let's have a closer look at the overall structure dimensions. Here you can see the height of the tower is said to be 5 feet tall for the model. The spaces between each floor is said to be 2 inches. The outer frames of the structure, including all the columns, were made to be 1/4 inch by 1/4 inch thick. However, the dimensions for the interior beams here are only 1/4 inch by 1/8 inch thick. The strategy here is to have all the functional beams and columns work together, as well as to minimize the weight of the building as much as possible.
Epicenter Engineering was contracted to perform the initial drainage study for the proposed Claremont Tower located off the 15 freeway on Claremont Mesa Boulevard. Through the study, it was concluded that the only existing drainage was located on the north side of the projected site, beginning on the corner of Ruffin Road and Claremont Mesa Boulevard. The site has a slope of less than 1% and leaves watered down an existing gunite ditch, parallel to Claremont Mesa Boulevard, to a Type F catch basin with an inlet located on the center divider of Claremont Mesa Boulevard. The existing catch basin has seen much erosion, with existing utility lines being exposed at its main source. The existing site has an elevation change of about 10 feet, acting as a natural way to route water from the south side of the site to the north side of the site to the existing gunite ditches located on Claremont Mesa Boulevard. The proposed site will incorporate the idea of pervious concrete, which will help eliminate and reduce stormwater runoff that will lead to the existing gunite ditches, as well as succulent plants located throughout the existing elevation changes in the landscape throughout. The pervious concrete system is intended to capture the runoff from the adjacent building and contiguous park-like grassed areas. Pervious concrete is constructed in layers, with each one made of different material and layered depth. Eco-concrete will be used that has a compressive strength of over 5,000 psi and excellent permeability in the range of 2.24 to 5.72 inches per minute. Pervious concrete can filter and treat infiltrating runoff, provide the load carrying capacity of conventional concrete pavement, and leaches environmentally beneficial calcium and alkalinity.
I'm going to go over the construction management portion of the Claremont Tower project. Areas focused on our project are scheduling, cost estimates, and codes and regulations. Scheduling focuses on the overall project. It breaks down this huge job that is building a high-rise structure into separate smaller jobs. Without doing this, it would be difficult to complete any project in a decent amount of time. The key to making an effective schedule is looking at all the jobs that need to be completed and figuring out what order is most efficient. This helps make sure that the workers that need to be on site are there working. Our schedule that takes into account men working for the construction company, how many days were allotted to complete the task, and how many days are left. It also shows when the next job is scheduled to begin. An estimate of how long it will take for the project can be determined by taking the sum of each individual job time. For the Claremont Tower, it should take 12 years. However, this is very reserved and with a larger workforce could be completed within 3 years. Estimates are another area of construction management that we're focused on. As you can see from ours, we focused on resources, labor costs, and material costs. With this info, we came up with a grand total estimate of $191,439,936. This is typical for the building of this size. The last area we focused on was codes and regulations. This area is for the contractor on site. It is a standardized way of building, mixing, and preparing materials. This is very important because the building we are constructing is intended for the public and must be able to survive natural weather such as wind, rain, and earthquakes.